before you commit to building a bulkhead. And then if you do find a site that is amenable or looks feasible, you still have to build them right and take into account a lot of things. So I'm going to kind of rush through, show you some of this stuff that we've learned over 30 years of digging around with a lot of abandoned mine sites. Source controls, as Rory was talking, like on the RICO project, we're looking for a way to maybe not treat as much water or not treat water at all, because that's an ongoing, perpetual type of a cost. When we build a big treatment plant in Colorado, the EPA will come in and build that. The state of Colorado and the taxpayers end up down the road running that treatment plant, and if you have to run it forever, if you add up those incremental costs, it costs way more than maybe spending a bunch more money up front to maybe either eliminate or reduce the amount of water you have to treat. So that's what we mean about source controls, and there's several types of source controls, and again, I'm just going to focus on bulkheads, but as Rory's talk was showing, there's ways to prevent inflows into the mines or prevent a small amount of very contaminated water from contaminating a lot of clean water. And we're always looking to get away from that end of the pipe perpetual treatment alternative to try to make it as cheap as possible. So what we have to do is change our focus to, instead of always an end of the pipe treatment thing, is what can we do to eliminate or minimize that acid rock formation that's going on that we saw from the chemistry and the geology underground. So source controls, there's several types. As I said, we can segregate clean flows, we can prevent water from running down big stopes and openings into the mine workings, and then we can also try to prevent outflows from the workings, so we can minimize the amount of water that we have to treat, or hopefully eliminate all of it. And that's where the bulkhead comes in. It's an outflow control type of approach. So the thing you have to figure out is, where is this going to work? And what we found in looking at a lot of ones that work really well and ones that don't work very well at all is that there's certain attributes that are very favorable that depend on the mine's geometry as well as the geology and the structural antithesis of the area that the mine is built in. And then I'm also going to talk a little bit about things that can go wrong. Even if you've got a good area for a bulkhead, what could go wrong if you don't anticipate where the water is going to go. So again, they're not going to work in all mines. They just aren't. I mean, everybody says, well, why can't we just plug all these adits up and be done with the problem? You've got to have an understanding of the site-specific mine and the groundwater system that mine is a feature within. So something was changed when we drove an adit or sunk a shaft. We changed that groundwater hydrology, and now we've probably got a short circuit going on. But you need to understand what's short-circuiting, where was the water before, what were the water levels before, where is the water going to go if I put the plug back in the mine. The other thing to do is, because we're looking at a feasibility analysis, is we want to proceed in a fail-safe type of approach where we're not spending a lot of money up front. We want to go incrementally and looking at certain things. So if you start looking at, I have no mine map and I think the mine is on a drift and all this stuff, you can really quickly realize, you know what, this is probably not a good bulkhead candidate. So by working through the types of things we're looking for, you can find a fatal flaw and detect that early in your bulkhead feasibility investigation, as early as possible, to try to save money on all the characterization work. And then the other thing to do is, before you ever come forward to build the bulkhead, you try to at least predict where is the water going to go before you build it. Because, as I learned, the rule of thumb is you never stop water. No bulkhead ever stops water. All it does is change the water's pathway. That water is going to go somewhere else. And you need to know where that somewhere else is before you build the bulkhead. Because if it comes out where you don't think it's going to come out, or something happens unforeseen, then that would be looked upon as possibly a failure. So the first thing is to understand the groundwater hydrology, and I've got a slide here showing some work that we did on a bulkhead up near Leadville. This is the Dinero Tunnel area, and you can see all the work that's being done on seepage, where we think the pre-mining groundwater tables were, where if we put a plug in, we might see locations where we're going to see seeps and springs reappear, because again, we know that something's going to change when we put the cork back in the mountain. The other thing that we want to make sure of is that we try to model where that pre-mining groundwater table was. And a lot of times there's clues from the actual mining history, from the descriptions of the ore deposits, whether it's oxidized or sulfide ore. We can get an idea of where that pre-mining groundwater table was. So site characterization is critical to success. You've got to get in and get dirty. You've got to drill holes. We've got to put in monitoring wells. In some cases, as you'll see, we've got to get back in underground. So some of the main attributes that we want to have is reasonably good access to the underground workings. If you've got a situation where you know you've got hundreds of feet of collapsed timbers and cave rock, and it's just, that's something right there that's going to probably prohibit you, if that's the only way in underground, of knowing how can we evaluate the underground system. The other thing that we're finding, and is pretty true, is that bulkheads really only work when you put them in the lowest hole in the barrel, the lowest spot on the mountain. If you put it up higher and there's other holes that are connected, obviously that's not going to work because the water's just going to go and flow downhill and come out in another area. And then we also want to do our homework and make sure that there's no other adjacent mine workings or drill hole connections into other properties. And that we found these lowest level haulage crosscut are much better than ones that, where if you look at it, if it's on a drain, or excuse me, on a vein or a drifted structure. What am I doing here? Half done. So what we want to do is not give up too quick. If we see that we have a nice crosscut tunnel, we might have had a mine map that showed that the first part of the tunnel was timbered, but then it's an open rock crosscut. Just because that's caved at surface, we don't want to give up too soon. And we've had some pretty good successes in areas of getting back through portal blockages and rehabilitating portals, and then we're getting into some really good underground workings, and we don't have too much issues with rehabilitation work. The mine maps are a must. If you don't have really good mine maps, if there's not really good understanding of what's going on, it makes the job that much more difficult because you're really just guessing. You really probably can't spend enough money on drilling to really figure out what's going on. And so again, mine maps are just a key to knowing where to be and what to look for. And so in this is an example. This is an example here of where we've got this. This is the Mary Murphy mine up by St. Elmo, and we've got two levels of nice cross-cut haulage tunnel, the 1400 level and then the golf tunnel level that come in. And then here's all the mine workings and the stope and the workings in here. So these then, using your mine map, become areas that you would target to see if it's feasible. Would a bulkhead work in these two types of mining works? Again, looking for adjacent mines or drill holes. The mine maps are very important. This is an example from, again, the Dinero tunnel. Whoops, hitting the wrong button here. So what we're doing here now is we're looking at our, where's the button? Here's the Dinero tunnel where we're interested in putting in a bulkhead in a crosscut that goes back to the vein, but we know we've got other mine workings around, and we want to make sure, looking at all available mine maps and exploration stuff, that we don't have any connections with any other mine workings. So what's the crosscut versus drifting that we've realized works well? Well, if you're on a crosscut, you're usually in a pretty good, better rock than what we normally find along these veins or these hydrothermally altered, sometimes fault fissure systems here. So if looking on a map of a mine, you can see that this is my lowest adit, and I've got this nice long crosscut haulage tunnel back to the vein workings. This could be something that might be feasible for bulkheading. As opposed to if you look at the mine map and you see that, well, this portal comes in right directly on the vein system here. So the portal is driven on the vein. There's stopes, there's ore chutes, there's raises to upper levels, and then also we usually find on these veins that we've got soft hydrothermally altered rock, lots of shearing, and it's really difficult to try to put a bulkhead in a situation here where if you try to cork this off, you're going to lose that water into the bad rock. It's going to be very difficult to seal up that whole structure where your adit's driven. The other thing we need to have is cover. One of the things you have to think about in a bulkhead is that you need enough rock cover to make sure that you're not going to have hydraulic fracturing or hydraulic water moving through fractures under enough pressure that it can get through. So if you build a bulkhead too close to surface and you don't have enough cover, the water is going to be able to get through those fractures and get around the bulkhead. You've got to make sure you do your calculations that you've got enough ground cover above where that bulkhead is. So the reason, and that's the mine stuff that we just talked about there. So I'm just going to run through some geologic attributes. As we talked about, we want solid, competent rock. We're trying to find an area in the workings that are minimally fractured. We don't have alteration or joints or large discontinuities where the water is going to leak into. The other thing that you got to be careful about is regional fracture pathways, large shear zones, faults, bedding planes, anything that could be that could cause a leak, so that this bulkhead you're getting water to follow a pre-existing natural pathway that you're not aware of, because that's where you're going to get a seep or a spring, or in some cases these fractures can lead into other mine workings some distance away. So here's an example of my make-believe Acme mine here. So here's this bottom level cross-cut tunnel, and then the upper workings here, you can see that they drove a tunnel in higher, and there's all this stoping on these veins, and this is the ore body that they're mining here. So before we do anything at this point, we've got a post-mining groundwater table that's all the water's running through the mine. We're getting a lot of acid rock generation, and the water table basically just comes right out of the mine in a pipe flow. So as Larry was saying, the idea would be, if we can find a good place to put a bulkhead, we can re-flood these workings back to the pre-mining groundwater table. But we need to know where that's going to be. So in this example, you got to be very careful. Am I going to back that water up high enough in the mountain that I'm just going to get another short circuit out of this other higher level? Perhaps that pre-mining groundwater pathway table is below that, and you can put in one bulkhead and get the whole thing back the way it was. In some cases, you may know ahead of time, yeah, I'm going to need 1 or 2 bulkheads, or maybe even more. But as long as you know that that's part of the feasibility analysis, then you can make that decision. Whoops. This is another example of what I call the multiple leaky bulkhead approach. This is one I worked on up in Montana, where we drilled from underground up to surface, and then we pumped the plugs back down through and put in multiple leaky plugs. And I say leaky because they do leak a little bit each one, but by the time you get to the portal, we had just a few gallons a minute of fairly clean flow from just the near surface fracturing. So then, if you do find a good place to put a bulkhead, obviously the last thing you have to make sure of is that you properly design the bulkhead and you follow proper construction practices. You got to make sure that it's going to handle the head pressures that you're predicting. You have to make sure that you can pump concrete way back in, or deliver that concrete to get a good product where you need that in the bulkhead and the working. So the mixture design and how you're going to actually place these deep underground bulkheads is critical. And of course, the other thing we have to make sure of is, once you place that concrete, you've always got to contact grout your construction joint, because all concrete, no matter how well you formulate it, is going to shrink once it cures. And if you don't treat that gap between the concrete and the rock after you put the plug in, it's going to leak pretty bad. So we got to do that, make sure we do that. And then in some cases, if you've got a lot of fractures and the rock isn't as good as you would hope, then you have to do this formation or curtain grouting, which is like what we did up at the Kohler, to kind of try to increase the bulkhead performance by filling up some fractures and cracks. So I'm going to show some other factors of safety that go into this. We need to make sure that you're like building a dam when you put a bulkhead in. It's an engineered pressure type of a situation where you want to take into effect seismic shaking and earthquake. You want to put in your overburden confining pressures, and make sure that your forms are adequately designed, that you've got a good pipe penetration to measure the pressure, because we need to monitor this whole thing while it's reaching equilibrium, because you still have one last ability. If it's not going to work the way you think, you can open up the tap and drain it off. Once you get back to equilibrium and things seem to be working, you want to make sure you abandon that flow through pipe, because eventually they will rust out and rot out and fail with time. So that's one of the last things you do in a bulkhead. And the other thing to make sure is you take into account the acidity of the water, because you've got concrete and steels, and you gotta take all that into account. So I've done my 15 minutes, and I'm just going to show a couple pictures of what these look like underground. You want to make sure you have a very clean surface. This is what it looks like behind the bulkhead before you pump the concrete. Different methods of pumping concrete. You can batch it on site, you can truck it in. This is the kind of state of practice in Colorado for bulkhead design, and we have all of this stuff on file should anybody need these designs. What it looks like when it's done. This is contact grouting the joint that I told you about, and in some cases you have to do the formation grouting. And this is where the rubber meets the road, where you get the grout into the fractures in the rock around the bulkhead and create that curtain around the bulkhead. And I don't really have time to go through all of these, but I'll put them up. These are the things that can go wrong. If you're in drift workings, you can't really seal a structure and they leak pretty bad. Bad ground just creates a lot of problems. You sometimes don't have enough money to just try to get it all corked off. If you put it too close to surface, the overburden thickness isn't great enough, and if you don't build it correctly and you don't do the work the right way, then you can still have leaks and things like that too. So the last thing I want to say is to make sure that you monitor everything while it's filling, and that at the end, be sure to grout and permanently abandon the bypass after it reaches equilibrium. Thanks.